In the frozen depths of the outer solar system, 500 astronomical units from the Sun, far beyond the orbit of Neptune, something is very wrong. The orbits of dozens of distant, rocky worlds out there seem to be tugged and twisted by an unseen hand. And according to our best models, the most likely explanation is a hidden planet silently circling the Sun on a vast, elongated orbit. This world could be up to 10 times the mass of Earth. And yet, we still can't find it. Astronomers have searched for this mysterious Planet 9 for more than a century. But every survey, every telescope sweep has come up empty. In an age where we can image planets orbiting stars dozens of light years away and glimpse the first galaxies born after the Big Bang, the fact that something this large could be hiding in our own solar system is deeply unsettling. But all this could be about to change. Last year, scientists found something buried deep in the data from a 40-year-old space telescope. They've combined it with information from a newer dataset, and now, with the first flood of discoveries pouring in from the Vera Rubin Observatory, they may have an answer. Is the hunt for Planet 9 finally over? The outer reaches of the solar system is a mysterious place, most unlike the inner region we inhabit. It's so distant that even if we set out at the speed of light, it would take more than 8 hours to get there. 9 billion kilometers is a long way. Upon arrival, we'd find darkness, peppered with unusual icy rocks, many of which we can barely detect, which we call trans-Neptunian objects, or TNOs. The first TNO was discovered by Clyde Tombaugh in 1930. I suspect you've heard of it. It's called Pluto. However, it took another 60 years until we found the next TNO, and an age of discovery began. Today, we've charted nearly 5,000 of these strange objects, but perhaps the most important find came in 2003, when a group of scientists led by Caltech's Professor Mike Brown decided to explore this outer realm. It wasn't long until they found Sedna, another dwarf planet, less than half the size of Pluto, but with an inclined, highly elliptical orbit. This led to an explosion of interest in the outer solar system, as scientists rushed to explain why its orbit was so unusual. If it were just Sedna, it could be put down to chance. But with the increased attention came the discovery of many more TNOs with equally strange orbits. Some crossed the orbital path of Neptune. Others moved in the opposite or retrograde direction to the 8 planets. Many were just greatly inclined. It raised the question, how did these orbits come to be? The only hypothesis that made sense of all of them is a 3-body interaction known as the Lidov-Kozai mechanism. It states that a near-circular but inclined prograde orbit can trade its inclination for eccentricity. But for that to happen requires 3 things: the Sun, the TNO, and a distant perturber. Mike Brown and his colleague, Dr. Konstantin Batygin, modeled the orbits of 17 TNOs and predicted that the chance of their movements being random was just 0.00006%. Instead, their model suggested that these objects were being perturbed by a mass they couldn't see. A planet-sized object, to be exact. Enter Planet 9. Now, we can model all we like, but the only thing that can prove this is actual observation. As they say, seeing is believing. You'd think, given that Planet 9 is supposedly in our solar system, it should be pretty simple to point our telescopes at where it should be and take a picture. But this is in fact exceptionally difficult to do. The brightness of a planet in the optical spectrum falls off at a rate inversely proportional to the 4th power of distance from the Sun, instead of the usual square of the distance. Because for us to see it, the already diffused light has to reflect back. Previous optical wide-field surveys from the Zwicky Transient Facility, the Dark Energy Survey, and Pan-STARRS 1 have all spent years hunting, but none of them have found a single candidate for Planet 9. However, there is something else we can look for. All planets we know of emit their own radiation in the infrared. A new team of planet hunters from Taiwan, led by Professor Tomo Goto and PhD student Terry Longfan, decided to take advantage of this and look for Planet 9 in two far-infrared all-sky surveys. The first taken by the IRAS, or Infrared Astronomical Satellite, in 1983, and the second by the Akari Infrared Satellite in 2006. The IRAS satellite conducted the first ever all-sky infrared survey above the obscuring warm blanket of Earth's atmosphere. Because of its vantage point and its ultra-cold sensor, cooled with superfluid helium to 2.5 degrees above absolute zero, it detected 350,000 new IR sources ranging from galaxies to asteroids. The Akari satellite was a similar design, but it had better spatial resolution and could record longer infrared wavelengths. The combined dataset of IRAS and Akari was truly huge, with 2.4 million objects found across multiple decades. Filtering this for Planet 9 candidates was a mammoth task. Fan and Goto had to track each object's position individually. Their strategy was to compare the surveys across time, looking for objects that had moved in a way the models predicted Planet 9 would. They were looking specifically for a planet somewhere between 7 and 17 times the mass of the Earth, with an orbital distance of around 280 astronomical units at its closest, or perihelion, and as far out as 1,120 astronomical units at its farthest, or aphelion. They also used that information to estimate the diameter of the planet and its black body temperature to narrow down their search further. Objects closer than around 500 astronomical units had already been searched by other groups, so Terry focused on the area between 500 and 700 astronomical units for his search. He then predicted what angular distance Planet 9 should cover in 23 years. He was hopeful. An object on a highly elliptical orbit moves much slower near its aphelion, so Planet 9 should spend more time out past 500 astronomical units, and therefore be in the survey area for longer. Any data from these two satellites that did not fit that prediction was discounted, and incredibly, from over 2 million data points, Terry was left with only 13 candidates. From there, he painstakingly whittled those down by eye, and was left with just one. It's hard to tell, but in the top left corner of the IRAS image, there are 7 pixels that are warmer than the background. And in the Akari image, taken 23 years later, the candidate has moved 47.5 arc minutes, the equivalent of 1.5 full moons, to the lower part of the image. Now, I think we can all agree that if we saw these images in isolation, we'd never guess what it is. But context is everything. We could be genuinely looking at the first image of Planet 9. Professor Goto says that if it is confirmed, he may allow Terry to finish his PhD early, which is probably fair enough. Much of the data surrounding this new candidate fits that expected of the proposed Planet 9. But there is some concern from Mike Brown and Konstantin Batygin about the inclination of the orbit of this new object being too steep. The team hasn't been able to completely map out how it moves, but Terry doesn't think we'll have to wait long to find out. The telescope set to follow up on these measurements is the Vera Rubin telescope, featuring the largest camera sensor ever created at 3.2 gigapixels. It's able to capture objects that are orders of magnitude dimmer than previous optical sky surveys, and scientists believe that it could increase the known objects in our solar system by up to a factor of 100. Its early commissioning data has already delivered over 11,000 new asteroids, including hundreds of distant TNOs never seen before, proving the power of its revolutionary detection pipeline. The telescope's 10-year-long Legacy Survey of Space and Time, or LSST, is now scanning the night sky to look for solar system objects, generating 20 terabytes of data in a single night. Give it a few years, and we might know for sure if this is Planet 9. But in the meantime, Terry, Professor Goto and their colleagues are not resting on their laurels. By filtering for the predicted parallax of a Planet 9 in the Akari data, they have in fact already found two other possible candidates. One way or another, they are pretty sure that if Planet 9 is out there, they'll find it. Of course, not everyone is as confident. What if measurements show us it's not there? What then? Surprisingly to me, given the many orbital behaviors a theory needs to explain, there are several possible hypotheses. The first is of a new belt, a scaled-down version of what we see around a galactic center. 2/3 of spiral galaxies, including our own, are what's known as barred spiral galaxies, with a bar-like central region composed of millions of stars on aligned and highly elliptical orbits, known as X1 orbits, around the center of the galaxy and its supermassive black hole. These orbits emerge out of group dynamics, lots of small interactions, rather than one big one. Almost like a murmuration of birds. Many tiny interactions between the individuals leads to coherent, beautiful movement without a conductor. In our solar system, we may find an equivalent, known as a Zderek-Madigan, or ZM, belt, named after two scientists who proposed it, Dr. Alexander Zderek and Dr. Anne-Marie Madigan. What we would expect to see around our Sun if it had a ZM belt is what we see now, clustered elliptical orbits. And it's proposed that Sedna and other TNOs are actually part of that belt. In this hypothesis, a singular massive body like Planet 9 is not needed if the combined mass of the ZM belt is more than 10 to 20 Earths. Even better, the LSST program at the Vera Rubin Observatory will be able to detect if this belt exists or not. But there is a third explanation that will never be directly seen by any telescope. The cosmic equivalent of a hit and run that happened a very long time ago. The culprit here could have been another star passing through. The gravity of the object could have tugged on the outer bodies disturbing their orbit enough, and in such a way, to cause the behavior we see today. But what if it wasn't a near miss? What if the object didn't escape? What if instead of a passing planet or star, our solar system captured a primordial black hole? That may sound implausible, however. It has been proposed that this is indeed not just possible, but around as likely as capturing a planet of equivalent mass. Primordial black holes are believed to have formed in the dense expansion phase of the Big Bang, and do not have a strict weight limit like those that are formed by a collapsing star. So one with the mass of a planet can exist, and would be about the size of a football. Impossible to see from Earth, unless of course it's consuming something. One final possibility is that we need to rewrite the laws of gravity. Proponents of modified Newtonian gravity, or MOND for short, claim that their model explains our current observations of the clustered TNO orbits. The increased pull from the galactic center under a MOND model is calculated to align the orbits towards it, and that's what we see. Now there are issues with MOND, which I won't get into here, but it's curious that it could provide a good fit to the data for the TNOs in the solar system without needing a Planet 9. Planet, star, black hole, or gravitational rewrite, what do you hope we'll find? Let me know in the comments. Personally, I hope it's a planet. For those of us who grew up and learned all about Pluto before it got downgraded, it would somehow be nice to go back up to 9 once more. And who doesn't want to complete our understanding of the solar system? Regardless of what it is, the Vera Rubin Observatory is now searching, and we're going to know for sure very soon. I can't wait to see what is out there. So tell me, does the thought of a hidden giant reshaping everything we know about our cosmic backyard fill you with the same electric wonder it does me? Drop your thoughts below. Subscribe so you never miss the next chapter of this unfolding mystery. and share this journey with anyone who still looks up at the night sky and feels that ancient pull of the unknown. The universe is waiting, and so is Planet 9.